Good afternoon, everyone. We'll continue today from where we stopped in the last lecture. Uh, in last lecture, we introduced the solenoid, and we have shown why the magnetic field in the core of the solenoid is concentrated, while the magnetic field outside the solenoid is close to zero, very weak outside at the sides of the solenoid. Then what we have seen also that the magnetic field for the solenoid would look like would be similar to the magnetic field of the bar magnet, with the only difference that the bar magnet is a permanent magnet and the solenoid is a temporary magnet. The magnetic field disappears once we switch off the current into the solenoid. So now we'll move to calculating the mutual magnetic force between two wires. If you recall, we've mentioned that the magnetic force can be applied between two parallel wires that are either having currents going in the same direction or in the opposite direction. And we said that the approach we would be taking in that case is, as you can see here with the pointer, we can calculate the magnetic field from one wire that is affecting the second wire, and then apply the magnetic force equation that will have the relationship between the generated magnetic field and the current of the second wire. So we will see how we do this. Now, before I start solving, I just want to mention that this is how are the wires are being uh, displayed here. I will be looking from this side. I will be looking from this side of the wire for simplicity in my derivation for the magnetic force relationship between those two currents and two parallel wires. So I'll start first with writing or drawing the current I2 and then my current I1, taking both of them going in the same direction. And I will put my coordinates here such that this is X, this is Y, and then Z is going out of the screen. Move it a bit. Let me do the other one in a different color. So this is I2. Everything related to I2 will be in red. This is I1. So if I am to put the equation for the magnetic force as F1 on 2 I will take the upper one as I2 and the lower one as I1. So if I say F1 on 2 is the magnetic force due to the magnetic field from wire number 1 on the wire number 2, then this one would be I2 L2 cross B1. So here I have the magnetic field generated by I1 along this circle that has the radius r. We can see that the magnetic field with the current out of the screen will take this direction. What does this mean? This means that at any point on this circle, the magnetic field will be tangential. So if I am, since I'm interested to find the magnetic field right at the wire I2, then the magnetic field B1 right on here will be tangential and pointing in this direction. So this is B1. So I have now B1 going into minus I hat. I have I2 also and I1 going into positive K hat. So if I am to write the magnetic field V1, it will be mu naught I1 divided by 2 pi r, and the direction would be minus I hat. This is B1. Now, in this case, F1 on 2 would be I2. Now, regarding L2 vector, L2 vector is L2 magnitude going into the positive direction. So in this case, it will take the K hat positive. So this is the L2 going into the positive direction of my coordinates. It will be L2 magnitude K hat. So I'll put it here, L2 K hat cross. Now B1 as mu naught I1 minus I hat divided by 2 pi r. So F1 on 2 equals 2. Remember the K hat cross out of the screen is positive K hat. So remember I hat cross J hat equals to K hat, right? This is the relationship. So I have here K hat cross I hat as J hat, and I have the minus, then the answer would be minus J hat, and then inside here would be, I will rearrange I1, I2, mu naught divided by L2 divided by 2 pi r. Notice that the induced magnetic force is in the negative y axis. So if I am to draw this now in blue, then this one would be F1 on 2. And also as a result of this, if you do the same, however, calculating F2 over F1, F2 on 1, you will get an equal in magnitude, opposite in direction force, because at the end, this force will be the contribution of I1 and I2. So both of them will have I1, I2, mu naught for the same length. L1 would be equal to L2. So the force would be also the same. In this case, what do you need to do? You need to calculate the magnetic field from I2 at the location of I1 exactly the same. So in this case, as I said, F1 on 2 equals to F2 on 1 in magnitude. So what can we learn from this problem? What we can learn from this problem is if we have two parallel wires that have two currents and going in the same direction, the magnetic force would be attractive. They will be attracting each other. If we have currents that are in a parallel orientation that are going in opposite direction, then the force will be repulsive. They will be repelling each other. Any questions so far? Okay. So this is the 3D visualization to what's happening. You can see that the force I calculated F1 on 2 always, yes, that's correct. If it's repulsive, they will be opposite. If it's attractive, they will also be opposite. However, they are equal in magnitude. Okay, so you can see here the 3D visualization. This is B1, the magnetic field B1, due to the current I1 right at the location of the wires 2. Also, forgot to mention that if you divide now this force by the length, you will be getting the force per unit length. It will be always, no, they will always be equal in magnitude because the force will be the contribution of both. So in both cases, you will have I1 times I2. If you recall the electric field due to the electric force due to two charges, both the charges contribute to that force, and this is exactly what's happening here. Both currents are contributing to this force. So you will always the length. This is L is the length of the wire that we are evaluating the magnetic force at. So you will always get the forces to be equal in magnitude, opposite in directions. However, both of the currents are contributing to this force. So it has I1 times I2. In all cases, even if the currents are not equal, they will be contributing to the same force. Okay. So as I said, if we divide this force by the length, you get the force per unit length. Now, this is what I was just referring to. If you have the two, this is the case that we have derived the magnetic force for. If both currents are going in the same direction, then the force would be attractive. If the currents are going in the opposite direction, then the force would be opposite in direction. However, both are equal in magnitude. Okay, now let's go to the next law, which is Ampere's law. If you recall, when we were studying the electric field, we looked at the cases where we had distributed charges that are symmetrically distributed. We said that we could have used the Gauss's law that takes a Gaussian surface around that surface for simplicity. We're making use of this Gaussian surface to have a uniform electric field on every point on that surface, and then calculating the electric field using Gauss's law. Ampere's law is similar in the analogy. We make use of the symmetrical distribution of the current, and then we take a path that is basically closed path, such that the integration of the magnetic field along this closed path will give whatever current captured by this closed path or crossing this path times the mu naught. So in this case, Ampere's law says the closed path integration of the magnetic field along this path equals to the current enclosed by this path multiplied by the permeability of the medium that this path does exist in. So the word along, the integration of the magnetic field along, is not far from the definition of the work, where basically you're taking the dot product, which means that you're taking the component of the magnetic field along the differential displacement. So in this case, when I say B dot dl, I mean the component of the B right on the dl. That's why when I take the dot product, I take the magnitude of both times cosine theta, which means it is as if I have projected the magnetic field along this path, which means the only component that is useful for me is the component that is along the differential element path. This is what the dot product, if you recall, between two vectors mean. So when I take the integration of the magnetic field along a path, this is what I have. This is what I do. When I apply Ampere's law, I have to take a closed path. This closed path basically define to me whatever is enclosed within that path, or in terms of the current times the permeability. So if I am to look at those two examples here, I have I want to calculate the magnetic field due to whatever current is within this path. Then in this case, as you can see, I am capturing no current. There are no current going into this path, which means that the magnetic field due to the zero current existing in this path would be equal to zero. Now, if I have this wire that has a current going into the page, and I take this closed path around surrounding this current, in this case, if I am to write the Ampere's law, in this case, the integration of this closed path for dl equals to mu naught times this current. So if this current that is enclosed within my path is assumed to be going into the positive direction, so if my axis is positive into the page, then this one would be written as I. If my axis is positive out of the screen, then this one would be written as minus I. Also, the other path will be also determined with the coordinates that you adopt within your problem. But at the end, Ampere's law says any closed path, any closed path, if it has a current going through, then there will be a magnetic field that is this current within this path multiplied by the permeability of the medium will basically equal to the integration of the magnetic field along this path. So it's a very convenient way to calculate this part of my problem, as we will see later on, because as long as I take a closed path, then I can refer to the total current enclosed by this path, as we will see in the coming example. So in this example, let me redraw the problem so it looks clearer to me. I'll open a new page here, and then I will say I have 1 ampere going out of the page. I have also 5 ampere out of the page. I have 2 ampere that is entering the page. Then if I take the red as my closed path A, then I took a different color for B, which is this. Then C between 1 and 5, and lastly D between the 5 and 2. Now the question is asking me to rank the magnitude of the first part of the integration in Ampere's law for the closed path A through D. So I'm not asked to calculate the magnetic field. It will be very cumbersome here because, as you can see, the path is not a symmetrical path with respect to the currents. So in this case, what I want to do is to calculate this part only, which means I'm only interested to find the mu naught E enclosed and rank them based on the right side of the equation, just calculating how much is the I enclosed within those paths. And by the way, those paths, there are like loops, and they only define a surface. This surface is an open surface. It's not a closed surface. It's only a surface. So that's a loop. That's a path that defines a surface, as we can see here. So if I am to rank those uh, in this integrate the left side, if I am to rank it, I would be looking at the total enclosed current. So let me first take my coordinates as, let's say, x, y, and then out of the page z. So my out of the page will be positive. I'll take this as my reference. So for mu naught, or let me say, since mu naught is the same, let me say the I enclosed at A, at the line A, equals to what? So let me see what are the currents that I have captured within this closed path. For A, which is the red, I have A capture, catching all of them. I have 1 up, 5 up, this is 6. I have 2 minus, and the total would be 6 minus 2 equals to 4 ampere. What about I enclosed at B? I enclosed at B. Where is B? B is the orange. I can see that B is only catching or surrounding the 1 ampere going up and the 2 ampere going into the page. So the answer is 1 minus 2 equals to minus 1 ampere. I enclosed at C equals to, C is, where is C? C is this. This is C. So this is C. If I am to calculate at C, C is having 1 ampere up and 5 ampere up. 1 plus 5 equals to 6 ampere. And then I enclosed at D equals to, D is having the 5 up and 2 N. So 5 minus 2 equals to 3 ampere. So now if I am to rank them, based on the greatest to the least, it would be C as the first one. C is the the greatest, and then comes A, and then comes D, and then comes B. So I have C greater than A, greater than D, greater than B, and the answer would be D. So again, so we have here B is the smallest, yes, because B is -1 based on negative because it's pointing into the page. Yes, that's correct. So we have here C is the greatest and B is the smallest. Any other questions? Okay. Yes, you could. Yes, you can use whatever direction that you want. I picked the direction to be. It was meant to be up this way, but yeah, if the direction was not given to you, then you can get the direction that you want. Okay, so back to here. Now let's apply Ampere's law on solenoid and see how do we calculate the how to apply Ampere's law to calculate the magnetic field for a solenoid. So in this solenoid, as you can see, we have the current entering from the top, leaving from the bottom. We have the path defined as a rectangular shape, as you can see, and we need to you apply Ampere's law to calculate the magnetic field in this case. So in this case, I will redraw the problem here. And again, you will see that the coordinates are very important in making your life easy when it comes to calculating when applying Ampere's law. So this is the cross section of the solenoid, entering, leaving. Based on the right-hand rule, you can see that the magnetic field is being concentrated and uniform inside, where I was given the closed path to be this way. So this is C, D, A, B, and this is L, and those number of turns within this L are N. I have N wires within this loop, and now I need to apply Ampere's law. So before I do this, I need to pick my coordinates here, and I'll pick my coordinates to be x in this direction, y, and in this case, you take x cross y is going to give you z entering the page. So positive is entering into the page. Now I can apply Ampere's law to calculate the magnetic field for a solenoid. So the first thing is the closed path integration for the magnetic field along this path equals to mu naught, and here I enclosed. So if I am to define dl, my dl is going to be along the x, so it will be dx. Direction is the positive direction, I hat, for path A to B. So I will start now this integration. I will discretize it into 4 integrations. So it will be A to B dl plus B to C plus C to D plus D to A equal to mu naught I enclosed. So I will start with the first integration first, which is A to B. We said that dl equals to dxi, and also B equals to B magnitude, also I hat. So the magnetic field is uniform in the x direction. I have the differential element also going into the x direction. So now I can apply Ampere's law. But before I continue, I would like to say that this path for B and C, since this path is perpendicular on the B, the dot product would be 0. And this other path that is also perpendicular on this uniform magnetic field, then the dot product between the differential element and the magnetic field will be 0. So I have this one, BC is 0. I have this dA is also 0. Now, what's left is the magnetic field outside here. We said that the magnetic field outside the solenoid is also 0 based on the derivations that we found in last lecture. So we will make this one as 0 as well. So we ended up with the following equation: integration from A to B for the magnetic field dot the differential element equals to mu naught I enclosed. Yeah, but they will end up later on canceling each other. So yeah, but the answer, if you're taking it for each, for example, that you make it tilted, then definitely it will have a component. It will have a component along this path. CD, the magnetic field we said outside here, the magnetic field outside and the solenoid is close to 0 or almost 0. That's why we said that this integration will be negligible with respect to the magnetic field inside the core of the solenoid. Okay, so now back to here. I have the integration from A to B for B I hat dot dx also I hat equals to mu naught. Now the I enclosed, the current enclosed, look how many we have. We have, let's say we have n wires, so which means that we have n currents. So this one is I, this one is I, this one is I, and so on. So we have n current that is captured by this loop. So in this case, we will substitute now the I enclosed with, now notice that the direction into the page is positive, Z. So that's why the current here is positive. So the I enclosed would be N I. That's correct. Yes, that's correct. So we end up writing the I enclosed being Ni positive, and then we will continue with the integration. So I have I hat dot I hat is going to give me 1, and then by the B is going to go outside. So I have B integration from A to B for dx equals to mu naught n I, which means what this gives x A to B equals to mu naught n I, and then B xb minus xa, and this equals to L, as we seen earlier on the graph, equals to mu naught and I. So this gives B equals to mu naught and I divided by N. So this is the magnetic field for a solenoid that is capturing N current inside. Now, if I define small n as the number of turns per unit length, then I can say my magnetic field magnitude equals to mu naught n I, where n is the number of turns per unit length. Okay, any questions so far? The B is uniform. B is a uniform. It's not a scalar. It is a magnetic field. However, it has a magnitude and it has a direction. However, here the magnetic field is uniform and it's along the x-axis, but it's not a scalar. It is a vector field. However, it is a uniform vector field inside the solenoid, the core of the solenoid. BC negligible because the path is perpendicular on the magnetic field. This is the same for BC and for DA as well. The small n is number of turns per unit length. Number of turns per unit length. Now, this L is capturing an N. This L is capturing an N capital number of turns, right? So if you divide this N by this L, you get what's called number of turns per unit length. Number of turns per unit length. So you're getting the rate. This is the rate. This is the rate of this solenoid, number of turns per unit length. So this amount of length is gonna give you this amount, this number of turns. If you increase the length, you're gonna get more number of of turns that are captured within the Amperes law. Yes, you can look at it in that sense. The higher number of turns per unit length, this means you have more turns in this specific length. Okay. So let's look at this example as well. You probably should be able, by inspection, just by inspection, looking at this problem, to know how to arrange the integration of the magnetic field along the differential element on those closed paths equal to. So all of them are enclosing this current I. So if I take the my coordinates, for example, to be x, y, and z, then all of them are enclosing this current I, except for path B. Path B does not enclose the current I, which makes A, C, and D are equal, and all of them are greater than the B, which is 0. And yes, you are right. It is B. Okay. Any other questions? The next laws would be Faraday's law and Lenz's law. Those two laws are incorporated together, as we will see. So what does Faraday's law state? Faraday's law says that a time varying flux that is crossing a loop will result into an induced electromotive force. Lenz's law, as we'll see later on, is responsible for the negative sign introduced here between the variation of the flux and the induced electromotive force. We will talk about that shortly. But before we do this, let me first explain how does Faraday's law work. So, as I said, let me first start drawing a loop. This is a loop that has an area A and a unit vector, normal unit vector, this way. And then I have a magnetic field B. Let me also choose coordinates for my problem here. So let me take this one, X, Y, and this is Z. So as I said, the induced electromotive force, Faraday's law, equals to the flux variation through this loop. So what does the flux mean? We've seen the flux before in the electric field Today we will talk about magnetic flux. And as you recall, the definition of the flux is basically in general given by the integration of a dot product of the magnetic field and the differential surface element for the area that you're interested to calculate the flux in. Now for this shape, since we have here a circle, then and the magnetic field, as you can see here, is uniform, I can take the magnetic field outside, and the dot product here would be, or I would say this equals to the magnetic field dot the vector A, where the vector A is basically as the area times the normal unit vector. So in my case here, according to the coordinates that I have, I can say that this A is A j hat. And also the magnetic field is pointing in the positive y direction, then this one is B j hat as well. Okay, so if this is my flux, it is the dot product between the magnetic field and the area vector, then if I am to take the derivative, this would be minus d over dt for B dot A. And this gives minus, which is dB, the derivative of the first, dot A plus B dot dA over dt. Now this is assuming that both functions can be time-dependent functions. What does this mean? This means if I am to look from this way in the direction of the minus z, if I am to look from the direction of the positive z toward the minus z, what would I see? I will see that this loop and here is the axis where this loop can rotate, and this is the normal unit vector, and this is the magnetic field. Now, here, the derived electromotive force if I'm to start with the dB over dt dot A, it means either the magnetic field here can vary with time, and the loop is stationary. And in this case, if the magnetic field is the one that varies in time, go by increasing and decreasing in the same direction, Then in this case, while the loop is stationary, in this case, I will call this technique as transformer electromotive force. So this one would be transformer electromotive force for dB over dt dot A. So I have the magnetic field varying with time while the loop is stationary. Now the second case is my magnetic field. So this is case one. Now the second case is I have the magnetic field being stationary and the loop is rotating in an angular frequency, for example, which means that the effective area with time is changing, which means, for example, if this is a t naught, then this loop is gonna rotate like this at the second moment. In this case, I have an effective area at T1, which is less than the area at T naught. And this is how the area is being changing with time. In this case, I will call this technique as motional electromotive force. So we have two ways to induce electromotive forces. The first one is by having the loop stationary while the magnetic field is varying with time. And this is what we call transformer electromotive force. And the second one is having the magnetic field as stationary in time while the loop is seeing a change in its effective area that this magnetic field is crossing. In this case, the flux is going to change. In both cases, the flux is going to change, and I will be inducing electromotive force. Or I can have a way to have both of them varying in time. In this case, I will be looking at the summation of both techniques together. So this is how we interpret Faraday's law. Now, when it comes to Lenz's law, Lenz is responsible for this negative sign. How is this happening? We will see in the next slide. Let's assume that this is my loop. And this is the magnetic field right at moment 1. This is the area, and this is the normal unit vector. This is at moment t1. Now at moment t2, which is the next moment, the magnetic field has increased at t2. The magnetic field has increased. At t3, the magnetic field kept increasing. Now what's going to happen? This increase in the magnetic field between moment t1 and t2 is going to result into an opposing magnetic field by this loop. An opposing magnetic field by this loop. Why? Because it tries not, or tries to resist any change in the magnetic field. That's why it applies an opposing magnetic field, trying to resist the change in the magnetic field. So the change here is increasing. As you can see, the magnetic field is increasing, going in this direction from right to left. Then the opposing magnetic field will go in the opposite direction, try to not to let the magnetic field increase. So this opposing magnetic field is going to result into a current. Remember the current. This opposing magnetic field, based on the right-hand rule, is going to result into a current going in this direction. So this opposing magnetic field, so now the current is going to increase. However, it will have the same direction. Now, the minus sign came to link B1 to I, because I is associated with the opposing magnetic field. And the relationship now between B1 and I will have the negative sign. Why? Because B naught is opposing B1, which basically means it's in the opposite direction, equal in magnitude. So it's going to result into a current generated this way. However, the relationship between I and B1 would be with a minus sign. And that's why we have the electromotive force equals to minus d phi over dt. And this minus basically is the link between the current and the external magnetic field that resulted into an opposing magnetic field trying to resist the change and the increase in the magnetic field, and this resulted into current going in this direction, as you can see, based on the right-hand rule. So the relationship between the I and the opposing magnetic field is based on the right-hand rule. However, because B1 now is opposite, now we have the minus sign that we have introduced here. Yes, the current is induced because of this opposing magnetic field that is trying to cancel the increase. The same thing happens when the magnetic field decrease. Then when the magnetic field becomes maximum like this, and now the magnetic field start now to decrease, the loop now will start to generate magnetic field in the same direction to try to not to let it decrease. Yes, it is. Yes. because when the magnetic field start to decrease, then the magnetic field, the opposing magnetic field, will also flip and will try to keep it the same, which basically will try to increase it, and that's why the current will flip as well. So we have here the increase is happening in this direction. So the increase is happening in this direction, and the opposing is happening in this direction. Now, once the magnetic field reaches its maximum, let's say now the magnetic field has reached its maximum, and now T4 at T5, then the magnetic field start to decrease. If the magnetic field start to decrease, now we have another magnetic field will start to go in this direction, trying to compensate for this decrease. And that's why, based on the right-hand rule, the flux now is this way. I have here the flux is that way. I have the current going this way. Now the flux is in the opposite way. I have the current also flipping in this way. So here I have the decrease happening in this way, and I have the increase now happening in this way. Yeah, of course. At the end, yes, this is the electromotive force generated by the variation of the lux. This is basically what's happening in the alternator. In the alternator, you have permanent magnets, and you have coils that are rotating due to the rotation of the engine, and this rotation is translated into an induced electromotive force out of this alternators in the curves. So this is one of the applications where you have a flux, you have a magnetic field, and then you're changing the variation, you're creating this variation in the flux by this motional electromotive force, and at the end you are going to get electromotive force out of the rotating coils. Okay. Any other questions before we move on? So, as I said before, this is the loop. That's the loop that has the normal unit vector. This is the loop. This is the closed path, defines an area, and this area has a normal unit vector, as you can see, and then as a normal unit vector, and then if you want to calculate the flux, it will be the magnitude of both times the cosine theta, basically between the normal unit vector on the loop and the magnetic field. So this is how we calculate the magnetic flux. So as I said before, you can achieve a variation in the flux using either concepts by having the magnetic field as uniform and changing the area, moving the area or moving the loop, and in this case you will be having a variation in the flux, or you can achieve it by having a constant and stationary loop and then a magnetic field that is varying with time, or by both of them at the same time. So it can be either of them, or it can be also both of them. But at the end, the main concept of generating electromotive force is to get a time varying flux. A is the area of this loop. A is the area of this loop, and this is the normal unit vector. So A is this area, and this is the normal unit vector on the area vector. So as I said before, this is what we have explained in that slide when we discretized the action that's happening in time. If you have a magnet that you're bringing closer, this means you are increasing bringing closer to the loop. This means you are increasing the magnetic field in this direction, increasing the flux in this direction. There will be an opposing magnetic field in the opposite direction. That's all that is going to generate a current. Now the negative sign is between this current and the external magnetic field, because this current is related to the opposing magnetic field, and the external magnetic field will be having this negative sign to link or relate this induced current to the external magnetic field. Okay, so let's stop here.